Okay, I'm just going to double check to make sure I got enough space. Yes, we got enough space. And we are recording. Yep. All right. Okay, so back to CISD 310. And let's see. It is 7:01. It's time to start. Are there any questions about the homework assignment? I see some smiles. Okay. Question?
It was
or
just,
is it specific to your program?
No, well, it was just once you have the mantissa and the exponent.
In base 2?
It was in base 10, and then trying to convert it to, never mind, the base 2 thing. It was just, let's see. It was just a lot. I'll go over it during lab. It's fine.
Okay, so what I can do today, is to kind of describe the overall strategy, because if you don't understand the overall strategy, the details becomes really difficult to get to. So let me answer the other questions. Go ahead.
So I just want to comment that your strategy for making constants in one and then bit shifting the left, it didn't really work at first because when you do one, it creates a 32-bit one. So you have to create a constant that's equal to 64-bit one, and then left shift.
Yep. Yeah, we kind of ran into that problem in class as well when I tried to demonstrate it in GDB. So as it turns out, GCC has exactly the same understanding of one being a 32-bit integer and not a 64-bit integer. So very good. Good point to bring up. Okay. So, let me just kind of repeat what he said. Let me get rid of this. So what he said is, when you say one left shift, 52 times or whatever, okay? This one, which is a constant, is understood by the compiler as a 32-bit signed integer constant. That's a default, okay? All GCC, all C compilers make a default of any constants that you spell out is automatically of the default integer type. In other words, there's an implicit typecasting like this of any constant that you spell out. Is that okay? Which is not good because what you really want is a unsigned long integer in this case. There are two ways to make an unsigned long integer. The first one, which does not require anything new to you, is just to specify the type ahead of the constant. That will force one itself to become a 64-bit unsigned integer. Okay? And because one operand of the left shift is already a 64-bit unsigned integer, the other side is only 32-bit, it will also coerce the other side to become a 64-bit number, and then the result is going to be 64-bit as well. So you only have to typecast one of the two operands to make the entire thing 64-bit. Is that okay? So the other way to do this is, which is not preferred, is to use UL over here, right after the constant. The C compiler would also recognize this to be specifying a 1, but as an unsigned long. But the question is, what is long? Because that is architecture dependent. Okay, so depending on what is the quote-unquote target of your C compiler, a long can still be only 32-bit wide. So you would need a long to mean a 64-bit. So I don't want you guys to have to mess around with that. So just use this notation. That guarantees that the first operand or the left side of the shift operator in this case is seen as a unsigned 64-bit integer. Okay, but thank you for bringing up that point because that can bite somebody in. Okay, so that's a good one. Any other questions regarding the homework or any? Yep.
What about the max? Do we do that as a?
Okay, then we have several maxes.
2 to the 53rd minus 1.
Okay, so that one it would be, you can just do it like this, okay, and minus 1. And if you want to make sure that the operators are in the right order, just put parentheses around it. Instead of typing 13 Fs. 0x13f would specify the same bit pattern, but this is easier. Makes more sense too. Any other questions about the homework? Okay. Any problems with the parsing part of it? Okay. So did you get it fixed?
No, I still can't get the word right.
Okay. So we can kind of talk about it during the lab time.
Yeah, that's what I didn't want to bring.
Okay, so for the parsing part, I can also give you guys a pointer. If you haven't done that part yet or it's not working, one thing that you want to do is whenever you have a loop, okay, so you can say, while, blah, 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 and, inside the loop, you're doing something. And typically, there are only 2 places where we need, or 3 places where we need a while, okay? Because when you look at the syntax of a scientific notation, you start off with an optional, plus or minus sign, but this is optional, and that's why we put square brackets around it. And just to be consistent with my notation, I put a backslash here to basically mean the plus is literal, okay? It is actually the plus sign that you can press and you can type on the keyboard. And then this is followed by a mandatory digit, okay? Usually people use an italic D to mean this is a digit, but to be consistent with the homework description, I'm going to use angle bracket here to basically say this entire thing is just a single digit, okay? Yep.
So you're saying that if there's a positive, you put a plus sign there?
Say again?
You're saying that if it's a positive number, you put a plus sign?
It is optional. You may or may not have the plus sign. So the default sign of the number is already a plus, but I can be explicit and actually put a plus sign there. I can give you some examples of what can be serving as the input to your program. So you have one single digit here, but then I use the plus symbol here. This one does not have a backslash, which means this plus is describing the syntax itself. It is not a literal thing that you're expecting in the number. This plus means whatever is before that, which is a single digit, there has to be at least one, but then it can have more than one. Is that okay? So plus is basically just saying whatever is before this, there has to be at least one of those. And then we also have an optional decimal or a point. And then after the decimal, we can have optionally any number of digits after that. And that is represented by something like this. Okay, well, I guess the asterisk can be a plus here, but it's okay. It can be a single dot and ends the entire number. It can also be a dot and then 5, 6, 7 can be a string of digits. And then we have an optional part that is specifying the exponent, which has to start with a lowercase e. And then after the e, we have an optional sign for the exponent, which can be a plus. And once again, I use backslash plus to mean that this is exactly what you can see in the string, as opposed to this plus here, which is just describing the syntax of a scientific notation. Or it can have a minus. And then after this, once again, you have to have at least one digit, but it can be more than that. So this plus here is indicating that we have at least one digit as the exponent, but you can have 2, okay? But in the homework assignment, I place the restriction that you can only have 1. Well, I only specify the quantity. I didn't specify that it can be, because I can give you something like this, right? That is still 5. Okay, so I read my instruction very carefully. Okay, so then that will close this bracket for the E. So this is the full syntax description of a scientific notation. So now I'm going to give you some examples of this type of syntax. Yep.
I have a question. So if the decimal and the E are optional, but can you have a digit followed by an E without a decimal?
Yes.
So 1 E to the 3rd power.
Yep.
That's possible.
That is possible. Okay, so we'll go with something simple first. Okay, 0 itself is a possible input. Okay, but I'm not going to give you this one because the logic that we talked about in this class cannot represent 0. So 0 is not going to be a test case. So if 0 cannot be a test case, well, I guess this can be a test case, right? Just below 3. Is that okay? because 3 does not have a sign, but that's okay because the sign is optional. 3 is matching this particular digit. It only says that we have to have at least one digit. 3 is 1, which is at least 1, so that meets that requirement. Everything after that are optional. We do not have a dot, which is optional. We do not have an exponent, which is also optional. Is that okay? So I can give you another one, -2. That's a possible input. It just has a sign, before that. +1 is a possible input, okay? Because you can have no sign, a minus or plus as a sign before the entire number. If there's no sign, then the implicit sign is a plus. Is that okay so far? Okay, so I can give you 1.3, okay, that's a possible input. It only has, I can give you 1 point, that's a possible input as well, because the digits after the decimal point is optional. Is that okay? I can give you 1 point and then an E and then a 2, that's a possible input. I can give you 1 itself, E2, that's a possible input because the decimal point is optional. I can give you 2E plus 2 because this plus sign here, even though it doesn't really do anything, it is also optional. It can be there. Okay. I can give you 2 point, okay, E and then a 2 over here. That's possible. And then just to make your life a little bit harder, but still be consistent with the homework assignment description, I can give you something like this, which is still meeting the requirement or the restriction of the homework assignment, because I said the quantity or the value of the exponent can only go up to 5 and can only go down to -5. I didn't say how it is going to be represented. Yep.
So for that last one, E002, so the exponent would be just 2, right?
Yes, it has exactly the same value as 2, but it is represented using the leading zeros as 002. Okay? But once you know how to parse, the first part, the rest is exactly the same thing. Okay? So I can give you like 233.03 E minus 003. Okay. And then just throw a plus here to use all the parts. So all of these are possible inputs. Is that okay so far with the notation itself?
Actually, isn't 233 too big? Because you said it had to be -10 to 10 exclusively with the digit. So
Yeah, this one will be too big. Okay. Fine. I said this can be what?
-10 to 10 exclusively.
Okay, so I can only give you one digit here. Okay.
You put 003.03.
Yep. I guess so. Yep.
So the exponent could be up to 1024, right? So it could be 4 places.
The exponent in the homework description, it has to be restricted to -5, -5 to +5.
Oh,
The value can only be restricted to -5 to +5, but I can still have leading zeros to get to the same value.
how many leading zeros?
But the logic that we talked about, remember on Tuesday, we talked about some pseudocode, well, actually they're not pseudo, right? Because they actually kind of see already. That logic would actually work with, just about any number. It's just the parsing part that has to handle, these, kind of special cases. Okay, so getting back to the parsing logic here. What is the strategy of parsing something that looks like that? It looks kind of complicated. I would break it up, okay? So personally, I would break it up into subroutines so that each subroutine can only handle like, something that is really simple. So I can give you guys like, a solution to one of them, okay? So the first one is parse, okay. It's probably faster for me to type it using an editor. So I'm gonna use an editor here. So the first thing I would do is I would create a structure or define a structure. Was it called parse10? It doesn't matter. You know, I can just use parse10, huh?
It was base 10 parse.
Base 10 parse? Okay, so we'll use that. Base 10 parse. And inside there's a pointer, right? So we have a const char ptr, or if you just want, if you want less typing, we'll just call it p. And then we have a mantissa. Okay, so the mantissa itself is un64 underscore tm. That's the mantissa for base 10. And if you want to make sure that the terms are easy to remember, so you don't confuse one with the other, you can make this m10, which means explicitly this is the base 10 mantissa. But I'll just use m here. You have an exponent. The exponent has to be an integer, and the width of this integer does not really matter because we are not going to exceed the limits of even a 32-bit integer. So this one you can just call it int if you want to. But if you want to be, careful, you can always specify the width. So this is e, but this is the exponent in base 10. And optionally, you can also have the denominator. So that part depends on how you want to represent the mantissa versus the exponent. Okay, so I can just simplify and only have these three fields. Okay, the idea of using a structure is so that you can define a variable of the type of a structure, and then you can pass the pointer to the structure into each parsing subroutine. Instead of parsing a whole bunch of parameters, there's only one parameter to pass. Okay? Yep.
Just in case anyone runs into the same thing I did, on the structure you suggested on the homework assignment, like the page, you used an unsigned int for the exponent, and when I did that, I was getting the wrong thing.
Because it cannot go negative.
But I didn't notice it because when I was doing printf, I was casting it as an int, so it's showing its value
okay.
as an int, as a
Gotcha.
signed int.
Thank you.
And when I switched that up, it was working fine.
Okay. So there's also an int for the sign too. Yeah, I missed that part. Yep.
This is kind of unrelated, but the last value you get is an unsigned 64-bit int, right?
What you're returning is an unsigned 64-bit int.
I'm just confused on how, I guess when you multiply all the bit shifted.
But you're not multiplying
Or
all.
adding.
When you're adding,
Yeah.
yeah.
How does that convert into? I guess?
Because all the bit shifting are applied to integers. So when you do a bitwise OR of all those the bit shift results, you still end up with an integer.
I'm just confused how it converts to a floating point.
The conversion to a floating point is not done in your subroutine. Your subroutine is returning a 64-bit unsigned integer, which just so happens to have the same zeros and ones in the right places as a 64-bit double precision floating point number to represent the value that is represented by the string as the input to your subroutine.
So your final value that you return should have the proper zeros to convert.
Correct.
Okay.
But if you look at the value of the integer, is nowhere close to the actual value that it is supposed to represent as a double precision floating point number. Okay? So when you have a structure like this, then you can have a subroutine, let's just call it a parse sign. Okay, this one is a freebie. If you choose to do it this way, okay. Okay, so if you choose to do it this way, you can borrow this code. If it does not compile, you have to fix the syntax error. Okay, so we are passing PTR as a pointer into this subroutine, which means in the subroutine, by dereferencing the pointer, I can change the structure pointed to by PTR. Is that okay? If you use C++, you can pass by reference, so you don't have to deal with the pointer in this particular case. But I'm sticking with just strict C here. All right. So the first thing you want to do is to give whatever you're processing a default. Okay. So you want to say, okay, if I don't see anything, then the sign is going to be the default. So the default of a sign is going to be. I'm just going to use 0 here to mean that it is non-negative. So this way, if I do all the shifting at the end, it's easy to process. Does that make any sense? Okay, so a 0 means it is non-negative, but if I do see a negative sign, then it will change it to a 1, because that is what you need as bit 63 as the final representation. Is that okay? All right. So the way I would do this is, I do not like the switch statement, but it does have, an application here. So there are two ways to do this. If you want to use a switch statement, you can do it. So you want to do a switch, PTR points to P, but you want to dereference that too. Just to be clear what we are dereferencing, I'm putting extra parentheses, but the parentheses are not needed in this case. In other words, we are always doing the dereference as the last operation. Are there any questions about this particular syntax? No questions? Okay. If you do have a question about pointers and you're not familiar with the arrow notation, this really is the same thing as this. It's exactly the same thing. In other words, we are dereferencing the pointer, so it becomes a structure, and then we can use the dot notation. Oops, I forgot to erase the other one. Then we can use the dot notation to access one of the members of the structure. So they mean exactly the same thing. It's just that for notation purposes, most people use a dash greater than symbol instead of the dereference first and then access the member method. But they're equivalent. Is that okay? All right. So inside here, I'm going to use a case statement for each thing that I can possibly see. If I see a negative symbol, I will handle it in a particular way. If I see a plus symbol, I will handle it in a particular way. And then I will also have a default, which basically means, what if it is not a minus and not a plus? Well, it falls into the default. The minus symbol means that we are dealing with a negative number. So we'll say the sign is basically a 1. The bit to represent the sign is going to have a value of 1. And do not forget about the break statement in a switch statement. And then in this case, and also the default case, I really don't have anything to do. But wait, there's a little bit more things that I need to do. Okay? Because if I just do it like this, then I'm not keeping track of, what is the next character that we are processing? So every time you see something that you're recognizing and you just processed it, you have to increment the P member of the structure. So every time I see something like the minus symbol, because I'm processing this, and so I say, I recognize this, I know what it means, then you have to remember to increment the P member of the structure pointed to by PTR. So, you can, once again, there are several ways to express this. You can do it this way, or you can say, plus plus PTR points to P. So the other notation is PTR points to P. But in this case, the parentheses is kind of important because it basically says you're not incrementing the pointer PTR itself, you're incrementing a member of what is pointed to by PTR. Okay? And I believe that without the parentheses, the increment is automatically applied to the member and not pointer itself, but it doesn't hurt to make it really spelled out. I personally cannot remember the what's the word for that? The priority of operators, so I end up using a lot of parentheses just to make things clear to myself. Okay, what about the plus? Well, the plus doesn't do a single thing because the default sign is already a 0, but we're still processing that character, so we still have to remember to increment the P member of the structure so that we are ready for the next one. The default case has nothing to do, because in the default case, we saw something that is not a plus, that is not a minus. I do not recognize it. I'm not going to process it. And as a result, the pointer is not incremented. Is that okay? All right? Okay. And that's it. This is parse sign. Okay? Its only job is to parse the sign of the number itself. Yes?
You don't need to break after the particles?
No, you do not want to break under. Well, I suppose you can, but following through is going to be fine too, because the default case doesn't have anything to do. Okay. Any questions about parse sign? So I'll give you one more freebie, which is parsing the first part of the mantissa up to the decimal point, or the E, or the known character. We don't know how it's going to end. We just know that it's going to end with a non-digit. That's all we need to know. Okay? So with this one, I think all the parsing stuff can be done relatively quick. So I'm going to say this is parse mantissa. Struct base 10 parse PTR. And I'll make it very clear here. The second part is up to you. I'm giving you the first part. Okay? But the second part is no more difficult than the first part, because instead of cheating and well, I shouldn't say cheating, but instead of making my job easier by looking at the description of the homework and say, oh, this is a special case, I only have to make my program work with the homework assignment. Instead of doing that, I'm going to do it in a much more general way. So basically, I'm saying, oh, what if there's no special rule for this homework assignment to make it easier? Okay, so I want to make it work in the general case. Okay, so in the most general case, you basically say, okay, I want to stay in the loop as long as something is true, and as long as we're in the loop, we have another digit to process. Okay, I'm pretty sure most of you have loops like that already. So the key question is, what do we put in the condition, and also how do we code it in the body of the loop? Okay. So we'll code the body of the loop first, because the condition is actually the tricky part. So I want to do the easy part first and then go back to the tricky part. So if I know that ptr dot dash greater than p is pointing to a digit, I can just keep track of a local variable. So I'm going to give myself a local variable u, and this has to have the same type as the mantissa itself. So we'll just call that TMP for a temporary variable. And that has to be initialized beforehand, so we'll initialize it to 0. Okay, so now we can just say, since we know for sure that ptr.p is pointing to a digit, so we just have to say, okay, so how do we keep track of TMP so that we keep processing the number and know the value of the number? So for this, I'm going to show you an example on the whiteboard. So let's say the input is 427, okay? So how do we parse the decimal number 427 to get to its value, instead of seeing it as the ASCII code of 4, followed by the ASCII code of 2, followed by the ASCII code of 7. And by the way, the ASCII code of 4 is not 4. Okay, so you have to differentiate what is the ASCII code as opposed to the value represented by a digit. So for each digit, there is the ASCII code, and then there's the value of the digit, and they are not the same. Okay, so I look at the 4 first, right? Remember TMP was 0. Okay, so this is tracking TMP. So when I process the 4, I say, well, 0 times 10 plus 4 is 4. So now temp is 4. Then I move on to process the 2. When I process the 2, I multiply TMP by 10, so it becomes 40. I look at the value of the digit that I'm seeing, which is 2. I add that 2 to 40. Now I end up with 42. And then I move the pointer to point to the 7, the digit 7 in ASCII code. Then I multiply 42 by 10, which is 420. Then I add the value of the digit that I'm seeing, which is 7. So now I end up with 427. Is that okay? So now the question is, how do I make this magic happen? Because it seems like TMP is just magically becoming like the value that we see in the string, and all I do is move the pointer from left hand side to right hand side, incrementing the pointer. Okay, so how do we do this? So you say TMP equals to TMP times 10, because you are seeing a new digit. So everything that you saw before needs to be multiplied by 10, because you have one less significant digit at this point. So everything is now more significant than it used to be. Is that making any sense? Okay, so you have to, basically this is the same thing as a left shift, but in base 10. Then you have to add to it the value represented by the digit that you're currently seeing. Okay? That is not going to do the trick because the ASCII code of 4 is 32 plus 4, which is 36. I think 20 is actually 0, so that will make, what is it, 3?
The ASCII code of 0, 48.
Is it 48? So this will make it 52.
Yeah.
Yep. So you cannot use, you cannot use that code because it's adding the ASCII code of the digit as opposed to the value of the digit itself. So what you need to do is to subtract it, right? That's all you need to do. You don't even have to look up the ASCII code of 0 because quote 0 quote is the ASCII code of 0. So you don't even have to look it up. Is that okay? Okay. So what do we do next? We just processed a character in the string, so I'm ready for the next one. So once again, we just add 1 to the pointer, not the pointer to the structure, but the pointer to the constar. So now we are in the next iteration, we'll be ready to process the next character in the string. Is that okay? Now, in order for this logic to work, PTR points, this P member has to be pointing to a digit, which means in order to stay in this loop, okay, I have seen this kind of logic a few times, so I would kind of like to just point out it is not a good way to do it. Or I should say, it is prone to having problems. Okay. So I can do something like this. Okay. So if I look at the syntax description, I can say something like that. So as long as it is not a period, which is the next thing that I'm supposed to see, keep processing, assuming it is a digit. Okay? It will work in some cases, but not in all cases, because the period is optional. Fine. Let's check something else first. Let's check something else as well. Okay, so we are looking at PTR.
Exclamation point equals. So you put equals to.
Oh,
period.
yep, not equal to, because if it does equal to, we want to get out of the loop. Okay. Then we say, well, it is not that and not that. We stay in the loop because, hey, we can skip the decimal point and go straight to the E. But that is not going to work either. Because I can give you just 3. Right? Then I can say, well, we know that this is a no terminated string, right? So there's actually a no character right here, so we can look for that too. And the no terminator is just a no, it's just a 0. You can just use 0 to represent a no character. Yep.
I thought that was risky because this was a while ago, but I read something that said you can't always assume a string is an alternated string. So is that?
That is correct. That's how we end up with a lot of security exploits.
Okay.
Yep. So this is not a good idea. Okay. So what do we do next? Because what we're doing here is we are thinking about what we should exclude. Instead, we should think about what we should include, which means as long as I'm seeing a digit, stay in this loop. Instead of saying, oh, if it is one of the things that is following a digit, get out of the loop. Change your mindset to think about what you should be seeing in order to stay in the loop. Okay? It's a digit. So instead of doing this, which doesn't address the issue of a no terminated string, instead of doing this, what I would personally do is to say that it is a character that has an ASCII code that is at least the ASCII code of 0 and less than or equal to the ASCII code of 9. So this way it is inclusive. Now, it still does not address the issue that you just mentioned. What if we don't see anything other than 0 and 9? It can keep going and going. So if you want it to be length delimited, then you have to have some kind of assumption and say that a scientific notation cannot exceed a certain number of characters. Then you can put a bound to it. But short of making assumptions like that, this is the best we can do. Is that okay? So this is, yeah.
Wouldn't that pick up the exponent too? Wouldn't that pick up the exponent?
Nope, the exponent will make it exit. It will exit when the P member is pointing to E itself. Okay? So this will stop. It has 3 ways to stop, assuming the input is correct. Okay, and assuming the input is a self-standalone string that is null terminated. So based on a lot of assumptions, it can stop when it encounters the null terminator. Basically, you're seeing something like this, it will stop. If you see something like this, it will stop too, because it will see the period, which is not a digit. It will also stop in this case because E, lowercase e, is not one of the digits. It will stop as well. What if we want to throw in something else? It will also stop. As long as it sees something that is not a digit, it is going to stop. Okay? So now you have to think about how it can stop in order to determine what you want to do next. Because if you see a period, then the mantissa is not done yet. You have some more processing to do. But if you see anything other than a digit, you're done. The mantissa is done. What if you see an E? Not my job. Pass it on to the next subroutine. Is that okay? So that's the usual thing, the usual thing that I would do for parsing is to kind of break it up like this. Now, I would think that this is the most complicated piece of parsing the digits. Okay, so once you have this chunk of code, you can either turn this into a subroutine, which may be helpful, or you can just copy and paste it. Because there are 2 more places where this code can go, which is parsing this part here, and also parsing this part here. So you can throw this chunk of code into 2 additional places. Now, obviously, what you'll be dealing with, okay, is not going to be the same. But since I'm only using a temporary variable, that part will still work. I'm not changing a member of the structure directly, so you will have to think about, what in the structure to change and how to change it. Is that okay? After you see a decimal point, okay, in the case of, okay, I'm going to throw a new case here. Okay, in a case like this, after you see the decimal point, you use the same logic to extract the value of 3 out of 003. But that's not the only thing you have to do, because you also have to keep track of the number of digits after the decimal point, because that will change the implicit exponent in base 10. So that code in the loop, you need an additional statement to keep track of the exponent in base 10. Is that okay? Okay, so this is the parsing part, and I'm hoping this will give you some additional clues of getting the parsing part done, because once you get the parsing part done, then you can actually move on to the conversion part. Any questions? Now, I just have to mention this because I had one program that I saw today that did the conversion right, but did not parse it correctly. So I was looking at the behavior of the program, and I go like, wow, it got the most complicated part done, but it wasn't parsing everything correctly because of issues with conditions like that. So that was a kind of rare case, because it got the most complicated part done, and it's just the parsing part that had some issues. Okay, so in addition to parse mantissa, I'm just going to give you a clue here. You will also have a parse exponent, and it's going to have the same parameters. And by the time you call parse exponent, then you are basically saying, okay, the pointer p should be pointing at lowercase e, or it should be the end of the whole thing already. And then you have to say, okay, if that is the whole thing already, there's no e, what is the implicit exponent? So you have to kind of think about that. All right, any questions about this? Questions about this part? What about the conversion part? Oh, that's right. I said that I would explain the overall strategy of the conversion. Okay. Okay. So basically, you start with something like this. Okay. You start with some kind of value. Okay. I'm going to use v to denote that value here. It has three components. It has a sign, it has a mantissa, and it also has an exponent in base 10. So I'm going to use the caret symbol here. Well, okay, to avoid confusing with the exclusive or bitwise operator, I'm going to use multiply to mean exponent. Or if you prefer, I can do this too. Which one do you want? Do you want double asterisk or do you want power? Power? Okay. So we are raising 10 to the power of some kind of e, which is the exponent in base 10. So after you parse the number using the code that I had just described, then you will have the sign. That's the easy part. It's either a 0 or 1 to mean it's negative or non-negative. You have a mantissa. The mantissa is going to be an unsigned 64-bit number, and you would use e to account for the decimal point here. In other words, when you see something like this, 2.003, the representation using this format would have 2003 as the mantissa, and then your exponent is going to be -3. Okay? And this -3 is counting the number of digits after you see the decimal point. The decimal point is right here. When you see this, e decrements by 1, decrements again, decrements again. I just spelled out what you need to add to that loop. Okay? So by the end of the parsing, you will have the sign, you will have the mantissa, which is a 64-bit unsigned integer. It may not use up all the bits, okay? Most likely it will only use very few of those bits. And then you also have an exponent, but the exponent is only specific to base 10. So your job is to change this so that it becomes the same sign, okay, sign never changes, but then the mantissa becomes a base 2 mantissa. I'll use M2 to imply this is in base 2, and then the power is no longer raised to 10. The base is not 10, it is now 2, with E2 as the new exponent, which is in base 2. Once we get to this form, the rest is fairly easy to do. So now the question is, how do we do this conversion? Well, you basically have to turn that E into a 0 somehow. Does that make any sense? So that means if E is less than 0, then somewhere in this loop, you are going to have to increment E. Is that making any sense? Because you want E to be 0, so if it's less than 0, you need to add 1 to it, once in a while, so that eventually you end up with a E that is exactly 0. Is that okay? But every time you increment E, it basically means that you are doing something to the mantissa so that incrementing E will balance that. Because you don't want to change the value being represented. V is still V. So if you're incrementing E, which means you have just multiplied the mantissa by 10, you have to do something to counter that. What do you have to do? So you have to do something to the mantissa, right? Divide equal to. Okay? If everything is easy to do, this is all you have to do. Okay? You divide the mantissa by 10, and then you increment the exponent by 1 to account for the division. Is that okay? Because when you look at the equation, or when you look at the value, okay, so first of all, we don't want to change the entire value. So value will still be the same. So we'll forget about the sign part because I just don't want to repeat the sign part here. So originally you have m times 10 to the power of e, right? Can I say this is the same thing as m times 1 times 10 to the power of e? Sure. Can I say this one is 10 divided by 10? Sure. This e is negative to begin with, so I want to increment the e. So can I say do it that way. I just separated the numerator and the denominator and regroup things a little bit, okay? Can I then change this to m divided by 10 times e, 10 to the power of e plus 1. Can I increment e? That's it. So that's the general idea, okay? We're trying to get e to become 0. So when e is negative to begin with, we want to keep dividing m by 10 and keep adding 1 to e until e becomes 0. But then we have a problem. What do you think is going to be the problem? You lose precision. At some point, you end up with a 0, and you cannot represent anything that is less than 1, right? Okay, so we have a problem. So with that problem, we can deal with that problem. So the way we deal with that problem is every time we divide it by 10, we'll go ahead and introduce something extra, okay? So we'll say, oh, this is no good. Okay, we'll divide it by 10, and eventually we'll also have e to the power of 10 to the power of e plus 1. Okay, but in between, I'm going to say, can we multiply another stupid one here? Well, yes, it doesn't do anything, but we can. Okay, so we still have to do this. And then can we express this one as some kind of power of 2 raised to the power of, okay, we'll just use p here, divided by 2 to the power of p times 10 to the power of e plus 1. Can we do this? Okay, it doesn't change anything, right? From the mathematical perspective, it doesn't do a single thing. So then we look at this and go like, can we associate, the top, the numerator of 2 to the power of p, and just link it with m? Okay, we're just using associativity of multiplication here. So we just say, okay, let's put these two guys together, and then put this one over here, and we'll have 2 to the power of p all by itself, and then 10 to the power of e plus 1 all by itself. Does that change a single thing? Does it change the value that we are representing? Did I mess up?
Yeah,
Oh, okay, I did mess up.
Negative or 1 over.
Yep, okay, so there we go. Okay, thank you. But the idea is that, okay, the idea is, okay, we're just moving things around a little bit. Okay. What is that becoming? Isn't that the same thing as that? Left shifting by m. Okay. But what do we do about this? And what do we do about this? We don't do a single thing. We track it. Okay. So what you need to do is every time you do something like this, you keep track of this. In the notes, it is known as p subscript I for iteration I. Okay. And this one is just incremented. Okay. So e basically is just increment by 1 for each iteration. Is that okay? But why do we do something like this? I mean, we still end up with a value of v. It's just that we introduce some really kind of seemingly unnecessary terms, but we still end up with v. The idea is if you divide something by 10, you lose precision. You end up with a value, but the value is no longer actually representing what it is supposed to be. Because from the mathematical perspective, a math professor will look at this and say, you're doing absolutely nothing to v. But to a computer science person, we'll say, we are changing what it is actually representing, because I did not put in one particular symbol here that makes the difference. This division is not a mathematical division where you divide it by 10, you get 1 point something. Okay, there's no fractional part after the division. There's an implicit floor function here. Every time we divide, there's an implicit floor. Okay, so there's an implicit floor here. There's also an implicit floor over here. So what is the big deal? We're going to lose something anyway. Okay, whether we do it this way or whether we do it this way, we're still losing something. But the proportion of what we are losing is different. In this case, whatever we are losing, has to do with the fractional part, but the proportion of that has to do with the ratio between the fractional part and the integer part. Is that making any sense? So when you look at the number, let's say for 42 divided by 10, okay? When you take the floor of this, it is 4, right? But 42 divided by 10 really is 4.2. So by dividing 42 by 10 and take the floor function of that, what is the error margin in this case? The expected result is 4.2, but what we got is only 4. What is the error margin? 5% is right, okay? So we have a 5% error, which is actually pretty big, because every time you do this, you're stacking up the error. So that's not good, okay? We don't want to lose your precision. We don't want the error introduced to be 5% each time we do something like that. What about this one here? Depending on what P is, right? So when you look at this particular thing, can I erase this part, the partial part? Okay. So when you look at this particular thing, because we are left shifting m by p bits, right? So we are basically multiplying m by 2 to the power of p. But you get to choose the p. As long as m left shifted by p times can still fit in a 64-bit unsigned integer, we're still okay, right? And what do you think is the largest value that is in the form of 42 left shift by some value p? What do you think this p is going to look like? Can someone just use mental math and figure out this p? You should be able to do it. You think about 42, and then you say, how many bits do I need to represent 42? 6 bits, right? Because 32 is not enough, that's 5 bits. 64 is another power of 2, and it barely covers 42, okay? So we need 6 bits to represent 42, so we'll just go ahead and say 6 bits here. Okay, and we are dealing with a 64-bit unsigned integer. That means the rest of the 64 bits can now be padded with zeros. Is that making any sense? So this is the only part where I can make a mistake because I cannot do subtractions really well. So I think we have 58 bits left, right? 58 plus 6 is 64. Yeah. Okay. So that means in this case, p can be as large as 58. Is that okay? And then we decide to divide it by 10 and take the floor function of that. So when you look at the fraction part of this number compared to the integer part of the division, what is the ratio? Is it going to be 5%? 0.5%? 0.05%? What is the magnitude that we are talking about here? Just roughly, what is the magnitude? We should be able to find out the magnitude of these things. What is the quantity that I can be potentially losing in this case?
1 over 2 to the 58.
1
over 2 to the 58th power.
To the 58th. I think it's potentially more than that. That might be the case. Okay, so what is the largest error that I can end up here? What is 42 left shift 58 times mod 10? What is the largest value of this mod 10? You don't need to do the calculator thing, I just need to know the magnitude. Worst case is 8, let's call it 9, right? Okay, so the remainder can only be as large as 9. What about the magnitude of this whole thing? 42 left shift 58 times divided by 10. It's a big number. I just need to know the magnitude. Okay, just give me a magnitude. Okay, so we'll just say, let's make it a worst case by changing this 10 to a 16. Okay, because now we're dealing with base 2. So if this is a 16, then we're losing 4 bits. So this is going to be some number like 2 to the power of 60 because we just lost 4 bits. Is that okay? So we are looking at a ratio like that. That is the worst case. How does this ratio look like in comparing that to 0.05, which is 5%? It's pretty small. How small is it? Well, let's go one step further. Let's look at the 9 because we're only concerned about the magnitude of things. So we can just kind of look at 9 as 2 to the power 3, right? So when you have a ratio of 2 to the power 60 to 2 to the power 3, you just cancel all both sides, and subtract or divide both sides by 2 to the power 3. So you have 2 to the power of 57 to 1. Okay, but this is all in base 2. I need to look at numbers in base 10. So how does this number in base 10? What kind of ratio are we talking about? So we do some more division. We do some more steps because each time you have a 2 to the power of 10 is about 1,000. Okay, so now you say, okay, this is approximately. Well, these are all approximate because we are just concerned about the magnitude of things. We're not really concerned about the actual value. So you look at the magnitude or the approximate ratio of this one, and you say, okay, how many 2 to the power of 10s do we have in 2 to the power of 57? 2 to the power of 10, the whole thing to the power of 5, okay, times 2 to the power of 7 is exactly that number, right? To 1. And then we say, well, we can look at this at 1,000, okay? So we say this is 1,000-ish to the power of 5. And then we keep 2 to the power of 7 to 1. So 2 to the power of 7 is 128. And then we have 1,000 to the power of 5. Does it have a name? Does anyone know? I'm pretty sure it has a name. Does anyone know that name? So we got kilo. Quintillion. Okay. Does it have a symbol? A T is a tera, a G is a giga, P is a peta. So keep going. Okay, let's not. Okay, if we don't know, we can always spell it out. 1, 2, 3, 4, 5 to 1. This is why we are shifting a whole lot before we divide it by 10. Because our error margin, even without the rounding and stuff like that, is now this. This is the precision of our division by 10 as opposed to this. And this is not even the worst case. Is that okay? I mean, does everybody understand why we are shifting it first until we get a huge number and then we divide that huge number by 10? Is that okay? So that is the main strategy, is to do it like this. You have to find what P works best in this case, carry out this operation. So for each iteration, it has its own PI, and then you have to add up all the PIs together so that you know totally how many bits you have shifted in the entire process. But because each iteration is also going to add 1 to E starts off with a negative value, so E eventually becomes 0. So now you have just converted this whole thing into, I think I can erase that, into something that only has an exponent of 2. There's no exponent of 10 anymore. And then at that point, V is still approximately, because it's no longer exact, okay? V is now sine times some kind of M2, a base 2 mantissa, times 2 to the power of some kind of exponent, but it is 2 to the power of E2. Okay, now implicitly, we still have E to the 10 to the power of E, except this E is now known to be 0, so it's not important anymore. Is that okay? So now when you have this, Okay, you know everything is now in base 2. So the last step is to make sure that this M2 fills up only 53 bits. So if M2 is more than 53 bits, shift it to the right until it is 53 bits. If M2 is less than 53 bits, or it needs less than 53 bits to represent it, shift it until it is exactly 53 bits. Is that okay? But every time you shift, you also have to adjust E2. Okay? So when you shift it to the right hand side, which is the same thing as division by 2, you have to remember to add 1 to E2. Right? If you shift it to the other side, which is multiplying M2 by 2, then you have to subtract 1 from E2 to balance, the shift operation. These shifting operations, so in the end, you end up with a 53-bit E2. Okay, this is your objective. Is you want to end up with a 53, not 52. Okay, it is a 53-bit E2. The reason why it has to be 53 bits is because the most significant one of this E2 is going to be tossed away. It is not explicitly represented in a double precision floating point number. Because when you look at bit 52, bit 51 to bit 0 is the fractional part of the base 2 mantissa. The 1 point is never represented explicitly. Is that okay? So that's why you want to end up with a 53-bit E2, where bit 52 is a 1. Is that okay?
That was third step?
I cannot remember. Yep, it's 3.3. 3.3 basically says you have your P already, and then you have your M already. So what do you do next? Yep.
So, but I believe for the homework, we have pretty small numbers, so this test would be sort of extra then, more general case.
It's well, for the small numbers, you still have a negative. You can have negative 10 to the power of -5 as the magnitude in base 10. So you can still end up with some pretty small values, and this would still be needed in order to get that part done. It's the opposite one that you can relax a little bit. When E begins as a positive number, then you can relax a little bit. Okay? But this is only here so that I can give you guys an idea of, just overall speaking, what are we exactly doing with those loops? Yep.
So once you get that number, you want to take 1 and shift it 52 times, or 53 times, and then subtract it from that number?
Yes.
Get rid of the 1? Okay.
To get rid of the 1, you can either subtract, or you can do an exclusive OR, because we know that bit should be a 1.
Okay.
Yep. So you can use exclusive or you can use subtraction. They should do exactly the same thing. Yep. All right. Are there any questions about what we have on the whiteboard at this point? No questions? Okay. What if E is non-negative or positive to begin with? Okay. I'm going to stay out of the whiteboard when people are taking pictures. Or you can wear a mask. Big helmet comes to mind.
Can't imagine which one. Said I can't imagine which one.
I want a big helmet that has an that is actuated, so you can flip the mask down and then flip it back up again, just like in the movie.
Like dark helmet?
Is it dark helmet or is it big helmet?
Spaceballs?
Yeah.
He flips out.
Is it dark helmet?
Dark helmet? Yeah.
Dark helmet. Okay. Spaceballs. Classic movie. I hope they make sequels to that too, just to address the additional episodes of Star Wars. Okay. So now we'll deal with what if E is positive? What if it is a large number? Okay. So this part does not have to change, okay? But from here, we'll change it a little bit, okay? Because E is positive, we want to decrease E by 1 for each iteration until E becomes 0. Is that okay? So to do that, I'm going to use a different color just so that I can, so it's clear that we are now dealing with a different case. Okay, so in order for E to decrement, I need to multiply M by 10. So now I'm going to associate multiplication by 10 to M. And then we can say, hey, we can do something like this, because division by 10 is the same thing as, oops, this is not E here, 10 to the power of E minus 1. Is that okay? Because division by 10 is basically 10 to the power of negative 1, and we can just decrement E by 1, that takes care of that. Okay? So this time it doesn't seem like we'll end up with a problem because, hey, we're just multiplying. We never lose precision when we're multiplying, but we do have an upper bound. You can keep multiplying, but at some point it's going to end. For your homework assignment, this E can only be within a certain range, so you may or may not have a concern. Okay, I'm not going to say anything. You may or may not have a concern. Okay, but what if E is really big? I mean, how big can this E be before we run out of digits when we're only using 64 bits? I think it's 16 digits in base 10. Okay, but we can do a quick calculation because you're dealing with 2 to the power of 64, and we're basically saying we're asking this question: it is approximately 10 to the power of what? That will tell you how many. What is the largest power of 10 that will still fit within 2 to the power of 64? We can use the same trick as before. So we look at this side as 2 to the power of 10, the whole thing to the power of 6. Times 2 to the power of 4, right? 6 times 10 plus 4 is 64. And each one of these is about 1,000. Okay? And this by itself is about 10 too, so we'll just call this another digit. So we're dealing with 18, right? Plus 1, which is 18 plus 1 is 19. Okay, there we go. So we're dealing with 19, okay? In other words, if this E is 19 or 20 or somewhere around there, okay, you won't have enough space in a 64-bit integer to represent the number. But remember, your mantissa only has 53 bits. So we are not even dealing with 64 here, we're actually dealing with 53. Okay, so when you look at 53, we just have to work these numbers out a little bit differently, right? And then we have a 5 here, and 2 to the power of 3 is 8, which is close enough to another 10. I'll just put a 10 here. So that gives us 15 plus 1, which is exactly 16 digits. That's what we saw last time. Is that okay? So anytime your E is in your base 10 exponent is 16 or above, then you can no longer just do nothing without division. You cannot avoid division anymore. Okay, so what we need to do here is we still want to keep this part as big as possible. We want to keep the mantissa with as many digits as possible. So every time you run out, okay, every time you say 10 times M is going to be greater than or equal to 2 to the power of 64, then we have to do something about it. Because we can no longer actually multiply the number by 10, because that number cannot be represented in a 64-bit integer anymore. Now you can change this to 53 if you want to, but I personally would make it 64 just so that we maximize the precision while we are doing the processing, and then we can just shift things out of the way at the end of the entire processing. Okay, so when this is the case, what do we do? Okay, if this is the case, then we better do something to handle it, because we do not have enough digits in base 2 to represent the result of the multiplication anymore. And by the way, this is not going to work in your program. So you kind of have to reframe that a little bit and figure out, how to detect that you are going to exceed the range of values that you can no longer represent it. Okay. So if this is the case, then we can go, well, we can still represent the value v, because now we'll just say that it is 10 times m times e to the power of e minus 1, okay, because this 10 counters the minus 1 of the exponent of 10. And then we'll say, well, multiply this by 1 again. But then this 1 is going to be some kind of power of 2 divided by some kind of power of 2. Just like before. But the idea this time is to associate the denominator of 2 to the power of p with the product of over here, and then leave the other one alone. So now I rewrite this whole thing, and I say, oh, okay, just to make sure the order is right, okay? So we have m times 10 divided by 2 to the power of p times 10 to the power of e minus 1. So we still end up decrementing the exponent of 10 by 1, which is the objective. And then we have some kind of dangling power of 2, which is 2 to the power of p. So this time it is just positive p instead of negative p, which is what we had earlier. Okay, is that okay? So to a mathematician, we haven't changed a single thing, right? The value has not changed at all. But to a computer science person, we have changed everything. And in fact, in this case, you want to do the division first, then you want to do the multiplication. The problem with the other way around is the multiplication is what is going to exceed the range of values that you can represent using 64 bits. So we cannot just say m plus 10, because that is the part that does not work. But when you shift it first, because when you divide m by some 2 to the power of p, and p is positive, it's basically right shifting by p. Now you have space to multiply the 10 to that number. Okay? The rest is still the same. Okay? So decrement the 10 exponent by 1 and keep track of this p here, which is what you need in order to make room so they can do that multiplication. Is that okay? And once again, we have a division. Every time we have a division, we're going to lose something. Because this is not a division like in all the math classes. This is an integer division, which means it is taking a floor function like that. When you have a floor function, it is not rounding. Can someone explain what is the difference between rounding and taking the floor or just taking the integer part of the division?
This goes down and rounding will go up depending on if it's greater than or equal to 5.
Yep, exactly. So when you say round 1.5, it is 2. When you say round 0.4, it is a 0. In other words, when you use the round function, half the time it will round up, half the time it's going to round down, assuming the fractional part has an even distribution, which it does in this case. Okay? But when you use a floor function, the floor of 1.5 is 1. So you're losing 0.5. The floor of 0.4 is 0. So you lose in 0.4. In other words, when you use the floor function, you're always losing some value. But when you use the round, sometimes you're gaining, sometimes you're losing. So on the average, you don't have a bias of only losing something in one direction. So that's why we want to take that into consideration in both cases. So how do you know whether you need to round up or round down when your integer division doesn't tell you which way to go?
The mod 10 thing is greater than 5, add 1 back to it.
Right. Well, that's division by 10. When you look at the division by 10, you do the mod first. You look at the remainder of the division before you do the division. Okay.
What would you say then? What was the question then?
The question is, in this particular case, how do I take care of the rounding? Because this division, the slash on integers is an integer division, which is implicitly also just taking the integer part of the division. not, so the fractional part is lost. So how do I know which way to round, so I can kind of account for that, so I don't have a bias? That's the question. What do you think? Not mod 2, we have to mod it with 2 to the power of p. So there's an easy way to look at to do this, but the math behind it is like this. So what you need to do is, before you actually perform the division, the first thing you need to do is to do a mod, okay? So you look at this. So we'll just call this R for remainder, okay? So if the remainder is greater than 1/2 of 2 to the power of p, can someone tell me how to express 1/2 of 2 to the power of p easily? Okay, if R is greater than or equal to 1/2 of 2 to the power of p, which is 2 to the power of p minus 1, you want to round up. If p is less than 2 to the power of p minus 1, you want to round down, which is automatic. So there's nothing you have to do in this case, but to round up, you have to increase the result of the integer division by 1, and that will take care of the rounding. But this is the hard way of looking at it. There's an easier way to look at it. What do we do when we do division? So instead of doing a division, there's a faster way to do division. It's called shifting, exactly. So when you do this, because this is eventually what you want to do, right? So the way to make this easier to deal with is you don't do it like this. You say, save 1 bit for later. Okay, so you say, m equals to m right shift by p plus 1, p minus 1, so that you are saving 1 bit. Guess which bit we are talking about? That is the bit that will determine whether the remainder needs rounding up, will lead to rounding up, or lead to rounding down. That's the 1 bit that we need to look at. So then what you do is you say, if m, after this operation, if m ampersand 1, round up. And then in the rounding thing, there are 2 ways to do it. You can either do it like this and just shift by 1 more time, plus 1, and then m gets m plus 1 or m plus plus, however you want to do that. And then the else case is going to be just m shifting 1 more bit, like so. So this will take care of the rounding. But does it make sense to you? Okay, we're dealing with base 2 numbers, right? How do you know R is at least 2 to the power of p minus 1? By looking at individual bits of R. You look at bit p minus 1 of R. If it is a 1, then it is at least 2 to the power of p minus 1. If bit p minus 1 of R is a 0, you're guaranteed that R itself is less than 2 to the power of p minus 1. That is why this bit, after we shift by p minus 1 times, this bit that we are singling out here is the same as bit p minus 1 of the remainder of the actual division that we want to do. Is that making any sense? Sort of? Okay. So I'm hoping this gives you an overall idea of how we are going to do the conversion and the rationale, the math behind the conversion itself. Which is not to say the C program is not important, but the concept is more important because you got to get the concept right first. Yep.
So for an else case on that, would you just shift it by 1 bit and then not add 1?
Oh, yeah, you have to shift equal to, but you are not adding 1 because in this case it is corresponding to a round down, which is automatic. So there's nothing you have to do. So this is This is shift equal to. Forgot about that part. How many people have seen this operator before this class? Okay, I think both of you took C or 360 from me.
Yep.
That explains it. That explains a lot of things, in fact. Well, this is called a, how about this one? I'm hoping most of you have seen this one. What is the general name of this kind of operator? If you were, compound assignment, that's exactly it. Okay, so if you want to look up all the things that you can do with compound assignment, look up the word compound assignment, C or C++, because some operators cannot be done that way. Negation is one of those. And I think the logical operators cannot do that either. You cannot have an ampersand equal to, that does not exist. But bitwise and does exist. This one does exist. Okay. So are you guys getting a better idea of how to do it in case you were not doing it before, but the program is not working somehow? Okay, but it's the idea that is most important, okay? So the most important idea ends here, okay? The core ends here because we just want to change this E to a 0. So now the question is, do we put this 10 over here, or do we put this 10 over here? But by changing that, you have to change the mantissa. So that's the whole idea. And then the rest is basically to preserve the precision or to make sure that we do not exceed what we can represent using only 64 bits. Is that okay? All right. So we are running out of time for the lecture, which probably means I cannot give you an exam next Thursday. Okay, I have to tell you what my original plan was. My original plan was to give you a long but rather just tedious homework assignment so that I can continue to talk about the processor, particularly the microcode engine of the processor, so that by today I would be able to cover enough material to give you an exam next Thursday, but only on the processor but not on floating point numbers. So I was only expecting to have to explain the floating point number thing using only one single class, and then leave it up to you guys to do all the programming because it's mostly just tedium. But that turned out not to be the case, so that's how it turned out. In the syllabus, they only allocated 3 hours to floating point representation, and I think we spent easily 4.5 hours on floating point representation. But I'm hoping that you guys now really know what floating point number represents, and you can do the conversion. There was one person, I cannot remember whom, but one person said that this kind of thing was being done at a graduate level at some university.
At Sac State, there's a graduate level course on just this.
Okay. All right. Okay, but then I have to tell you another story because it seems like we're doing a lot of stuff that is not that does not belong here. I have to tell you one story because there was one student who went to Sac State and she had to take one of the upper division classes, but she did not take the prerequisite class at Sac State. She took the prerequisite class over here. And so when she approached the professor who was teaching the upper division class that she wanted to take, she said, well, can I challenge the prerequisite because I think I have taken that class at AR, but not at Sac State. And then the professor just asked her, so who was teaching that class when you took that class? And then she said, well, it was TAC. And the professor immediately signed it off. So that's the plus side. That's the bright side of all this stuff. Got to look at the bright side, at least for the next 4 years. Uh-oh.
So does that mean floating point stuff's going to make it to the first midterm?
Say again?
Does that mean that floating point stuff like this is going to be in our first midterm then? Or is it just going to be microprocessor?
I still want to just stay with the processor, but this will be the next one. Yeah.
So we have 2 midterms total and then a final?
Yep.